Hey everybody, this is Larry. This is day 18? No, 9, no, 20. Man, I have no idea what's going on anymore. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about this one. Day 20 of the Leetcode June challenge. I am very tired today. I did a hill sprint, 4x400. Somehow total about like 7.5 miles today, including the warm-ups, cool down, and all these things. So I don't know, and it's very hot. That's the biggest thing. So I've just been very tired. So let's take a look at today's problem and see what we can do. Today's problem, we have 1552 magnetic force between two bores. Okay, so we have Earth C-137. Rick discovered a special. What is this? Rick and Morty again? Rick discovered a special form of magnetic force between two balls if they're put in this new invented basket. Rick has N empty baskets, the I baskets at position I. Morty has M balls and needs to distribute the balls in the basket such that the minimum magnetic force between two balls is maximum. Rick stated that the magnetic force between two different balls at X and Y is X minus Y. Given the integer array position and integer M, we return the required force. What does that mean? Okay, so here we have minimum magnetic force. Huh? Oh, a large. So you want to maximize the largest minimum force. Okay. That makes sense. I mean, I think these problems are a little bit, I don't know, it's fine, but it's just a little bit awkward because I think the difficulty about this problem is recognizing what kind of problem it is. But of course, the same thing that we did yesterday with binary search, it kind of puts the idea in your head, and in that sense, it takes away a little bit of it, right? And just giving binary search, the idea here is that there's a thing where you can brute force in a way. It's can you achieve a minimum of 1? Can you achieve a minimum of 2? Can you achieve a minimum of 3? ... And there you go, right? So that's basically the idea behind binary search, is that you first do a linear search, or like have the idea constructed for linear search, but recognizing that it only changes in one direction, right? Because the question that we're asking is, can we achieve a minimum of 1? Yes. And then yes, 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 yes. And then at some point it'll go from yes to no, and that's your answer. Or the last yes before the no in this case. And then here, of course, we would speed it up by binary search, because if it's true, then you could cut everything that's to the left, and if it's false, you could cut everything to the right, right? And so forth. And then what's left is that, well, can we figure out how to do the, can the minimum be X for some X in fast time? And the time in this case should be okay, which is that it should be okay, because you can do it in linear time by the idea of greedy. Because here, for example, you want to force minimum magnetic force to be 3, then, well, going from left to right, you always pick the first ball, which is in the first bucket, because you can. And then the next one is going to be, you know that it's going to be at least 4, but of course, also, that is greedy in that way, because you only need to satisfy a gap of 3, then make it as close to 3 as possible, right? Because then you can fit more balls in, right? So that's basically the idea. So it's again binary search. So yeah, so here we can say left is equal to 1, because the minimum is going to be 1, right? Yeah, because there are 2 balls. Because with 1 ball, I'm not sure how they want to interpret it, but 2 balls is fine. And then right, which is the upper bound for the magnetic force, it should be basically, I guess here, The other thing that we're not given positions in sorted order, so we have to sort the position, right? So then now the gap, the rightmost is going to be just the max element minus the minimum element. Probably fine, right? Because that'll work for m is equal to 2, and so forth. And here, as I say, I always like to have them inclusive. And this is always possible because the answer could always just be 1. As long as we have enough, as long as we have enough balls or whatever, or enough buckets or baskets, whatever they call it. Right? So this will always have an answer. 1 can be an answer, right? And then we set it up. Left is the middle, or middle is the middle, and then we go if good, right? What is good? What do we want good to be? Well, in this case, we probably want to define good as pretty naturally, right? Which is that we can figure out target magnetic force, right, or magnetic force of target. Maybe that's more grammatically correct, right? Yeah, and then here we will then say, wait, so if this target is true, that means that this is a possible answer, but you want to try a bigger answer, right? So then left is equal to mid, else, then you do this, and here to fix the rounding, oops. And there you go, as I always do. For this target, as we said, we're going to do greedy. And the way that we do greedy is, just how many balls is used. And then the last basket, we can maybe say is negative infinity. So that this will trivially be true for the first basket that we come across. And then now for B in position, B for basket. I don't know, the position is weird, but anyway. But yeah, then if B minus last basket is greater than or equal to target, then we can say balls is increment by 1, last basket is equal to B, and we're Gucci. And then we just return how many balls we used, which is going to be if we fit at least M balls in, right? Hopefully no silly mistake. We'll give it a 1, we'll give it submit. Apparently we did it 4 years ago. Did it correctly that time too. Okay. I wrote it a little bit differently that time though, but that is a little bit wild actually. Oh, because I did mid plus 1 for some reason. I think back then I still maybe was leaning a little bit on templates, but now I do it a little bit differently. I do binary search in a different way, which is that I always do inclusive, and I always just do this, and then I just figure out how to fill out here. But before I might have done something a little bit awkward. But yeah, what is the complexity here, right? Again, this let's say B is the number of bits representing the maximum element here in position. Then this is going to be log B times. For practical purpose, for this kind of these constraints, this is going to be only 32 or 31 or whatever, right? Give or take. So yeah, so over B times, over log B time, and of course each one of these does one of the call to good, which is going to be linear. So it's going to be just like 32 times linear, or n times B, or log B is for these. But of course you have to sort, so this is going to be n log n plus n log b, and that is just the answer. Yeah, that's all I have for this one. I'm curious what the hints are. Yeah, whatever, okay. That's all I have for today. That's all I have for this one. Let me know what you think. Thanks for watching. Stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye-bye.